We're asked to prove that x plus e to the x equals 0 has a solution on -1 to 0. And anytime you're asked to show something has a solution, but not necessarily asked to find the solution, a good place to start is the intermediate value theorem. Let's just make a graphical argument on how that might look, right? So I don't know what this function looks like, and I'm not going to think about what it looks like. All I know is we have -1 here and 0 here, and whatever's going on with this function, right, doesn't matter what's going on. That's the cool thing about these existence theorems. It doesn't matter. As long as we can show that it's continuous, that's the whole key. Then we're in luck. We then find a point that's less than 0 down here, a point that's greater than 0 up here, and then the intermediate value theorem tells us that there must be some point where it equals 0, which would be a solution. So that's the machinery of how this thing works. Let's take a closer look at the theorem and try to use it in detail. So the intermediate value theorem starts us out with, suppose f is continuous on closed interval ab, and L is some number between, but not equal to, f of a and f of b. Okay, so let's decode this. -1 is going to be our a, and 0 is going to be our b. Usually your interval will somehow be given to you. So our closed interval is -1 to 0. And how do we know that x plus e to the x? That's our function. So let's clearly define our function here. F of x equals x plus e to the x. Is it continuous? Well, we know that x is continuous. We could just use the continuity checklist on that. We also know that e to the x is continuous because that's on our list of continuous functions that we can always pull from. Remember, we have all these functions that we kind of accept are continuous. Some of these can be easily proven. Some of them are a little more challenging to prove, but look, polynomials, rational functions, trigonometric, inverse trigonometric, exponentials, that's where we are here. Also logarithmic, radicals, absolute value, and so on, right? So many continuous functions. Right now, though, we have exponential functions, which is what we need for this example. So e to the x is continuous. And we know that the sum of two continuous functions is continuous, thus f of x is continuous. It's continuous everywhere, including the closed interval -1 to 0. Okay, well, what's our L here? And back to the theorem, L is any number between f of a and f of b. So L is the thing we want to hit is 0. So L is 0 in this case. Okay, so let's verify that 0 is between f of -1 and f of 0. All right, f of -1 is -1 plus e to the -1. That comes to about -0.63. F of 0 is then 0 plus e to the 0. Well, that's simply 1. And notice that indeed L is between these, which are 0. So -0.63 less than 0, strictly less than. These have to be strictly less than. You don't want to be bumping up right on the endpoints. Theorem doesn't necessarily hold there. So -0.63 less than 0 less than 1. Okay, so we've proven that the function is continuous. Check. We've proven that L is between those points. So then we can say thus, by the intermediate value theorem, there must exist some point C in the interval of interest. So in -1 to 0, such that f of c equals 0. What that tells us is that there is some x value, we'll call it c, such that when you plug it in for x, you get 0, which means this thing has a solution. So we'll just write a nice conclusion here. Therefore, x plus e to the x equals 0 has a solution on -1 to 0. We have completed the proof. We can add in a little proof box if you'd like, right? Because we have proven this thing. So the way these proofs work is you have an if and then in these theorems, and you verify the if portion of it, which is all this stuff. It's not really written as clearly as we might like, but this is all the if stuff. So the way a proof works is you verify the if part of it, and then you get the then part of it as the result of the theorem. So we verified the if part, continuous, check, and L was a number between those two values for the function, check, and then we get the conclusion of the theorem, which is, in our case, a solution. One of the biggest murky points on these kinds of exercises is how much to say about the function being continuous. For me, for now, it's enough to check for yourself that the function is continuous and then mention as part of your proof that it is continuous. I don't want to get too far into the weeds about proving things are continuous because you can do that in a future course. But if you move forward with the intermediate value theorem without mentioning that the function is continuous at all, you're missing one of the biggest features of the if part of the theorem. So that would not be correct. You have to at least say a little bit about the function being continuous to justify using the IVT at all. So at least say something about the function being continuous, and maybe just a little bit about why, but you don't have to go too deep into the woods on that.